Hey grade 12s and welcome to this video. In this video, we're going to be going through the NSC November final exam. I would also like to say that I get these papers from stanmorephysics.com. They usually upload past papers a few days after they have come out. So you'll be able to find a number of past papers that you can use to just practice. So without wasting any more time, let's get back to the paper. So question 8.1 says, in the diagram, O is the center of the circle, and then MNPR is a cyclic quadrilateral, so this MNPR, and SN is the diameter of the circle, so that chord MS and radius OR are drawn. So we have MS, that's a chord, and then the radius OR, okay, but OS is also a radius and ON. Okay, and then they say that angle M2 is equal to 64 degrees. The first question is determine, given reasons, the size of the following angle. So we have to find angle P. Remember that they told us that this MNPR, that is a cyclic chord. So that is a cyclic chord. And what we know about cyclic chords is that the opposite angles of cyclic chords add up to 180 degrees. So to find angle P, we're just going to say this is 180 degrees minus angle M2, which is 64 degrees. And so angle P is equal to, that gives us 116 degrees. So angle P is equal to 116 degrees, and it's because of the opposite angles of a cyclic chord add up to 180 degrees. And that's the first one. Okay. Second question, they want us to find the size of angle M1. So we have to find angle M1. So to find angle M1, let's just see where M1 is. Also, when you found an angle, it is very helpful to put it down. So now that we know that angle P is 116 degrees, it will help you a lot to just put down that angle. Okay, so we know that is 116 degrees, but they want us to find angle M1. So depending on where it is at the circumference. And we know that, or they told us that, we had a diameter. So another helpful thing that you can do is always look back at the scenario just to see anything that you might have missed. So they told us that SN is a diameter. So since SN is a diameter, the angle supported by a diameter in a circle is always 90 degrees. And so since SN is our diameter, it means that this angle here is 90 degrees. That whole angle, this adds up to 90 degrees. And so to find M1, we can simply just say angle M1 is equal to 90 degrees minus this angle 64 degrees. Okay, so that they add up to 90 degrees. So minus 64 degrees, and let's see what we get. We get 26 degrees. So angle M1 is equal to 26 degrees because of the angle in a semicircle. Okay, so moving on, last question in this 8.1. We have 8.1.3. We have to determine the size of angle O1. So remember that we have this angle over here now. M1 is 26 degrees, which we found, 26 degrees. And now we have to find O1. Okay, so if you look at M1 and angle O1, you'll see that these two angles are being supported by the arc SR. And so since angle O1 is the angle at the center, and this is the angle at the circumference supported by the same arc, O1 will be double the size of M1. So O1 is actually equal to 26 degrees multiplied by 2, which is 52 degrees. So you can even just go ahead and say O1 is equal to 52 degrees because of the angle at the center being twice the angle at the circumference supported by the same arc. And I'm just specifying the angles and the arc. Okay, next question. So now we are on 8.2. Okay, so in 8.2, this is what we have been given. They tell us that, so in the diagram, ABG is drawn. So this is ABG. D and E are midpoints of AB and AG. So D and E are midpoints. And then we have that AG and BG are produced to C and H respectively. F is a point on BC such that FG is parallel to CH. So these two lines are parallel. And the first question is, we have to give a reason why DE is parallel to BH. So why these two lines are parallel. Okay, if you look at this diagram, you have a triangle, and in this triangle, you have a midpoint here on this line AB. So this is equal to this, and that is equal to that. This is the converse of the midpoint theorem. This is what can be used here. So if we have to tell them why those lines are parallel, 8.2.1. Okay, for you to remember how this works, the midpoint theorem itself, you'll be given a triangle and then you'll be given a line here. Now, in the midpoint theorem, whatever this is called, let's say it's called ABC and this is DE. If you have been given, so you always have to, in every Euclid theorem, you have to take note of what have I been given and what do I have to conclude because of what I've been given. So you've been given that in the original theorem, the midpoint theorem, you'll be given that AD would be equal to DB, and you'll be given that DE is parallel to BC. So see that this is what you are given at first, and those two are parallel. And what you would have to conclude, and let me actually put that in red, what you would conclude from this is that AE is now equal to EC, and that BC is twice the size of DE. That is the midpoint theorem itself. Then the converse of the midpoint theorem, this is what the converse states. If you've been given a triangle and a line drawn to the triangle, but this time it's not parallel to the triangle. Let's say this is called A, B, C again, and D, E. In the converse of the midpoint theorem, if you are being given that this is equal to this and that is equal to that, then what you will conclude is that DE is now parallel to BC, and BC is twice the size of DE. So it all comes down to what have I been given and what do I have to conclude. And the reason for this would be the converse of the midpoint theorem. So that's exactly what's going on here. You have to just focus on what have I been given. So in 8.2.1, the reason why those two lines are parallel is simply because AD is equal to DB as it has been given, and also because AE is equal to EG. That's the reason why. The minute you have given them a reason why these two lines are parallel, you can go ahead and say that they are parallel so that you will remember to use them like that. Okay, next question. We have that 8.2. If it is further given that FC over BF is equal to 1 over 4. So FC over BF. Okay. So immediately they start giving you ratios. It is better to put it on the diagram since they said FC over BF. So we're looking at FC, and that is 1. It's not the length of FC. It's just the ratio. When you take FC and you put it over BF, it simplifies to 1 over 4. So it's just really speaking about how these lengths are being shared in this line of BC. Whatever the length of the line is, FC is taking 1 part and BF is taking 4 parts. That's all it's saying. So how you can put that down for you to remember, we can call this, so let's actually just call this 1A, and then we'll call BF, that length, we'll call it 4A, meaning it just has 4 parts, 4A, okay. And then let's see what else they say. They also say that DE is equal to 3x minus 1. Now notice this is not a ratio. It's not a ratio because it has not been put as a fraction or as a ratio as like 1:4, something like that. This is just the length of something, but then we don't have x. So DE is equal to 3x minus 1. So DE 3x minus 1, okay. And then they also tell us that GH is x plus 1. GH, this, okay, is x plus 1. So x plus 1. And then they say calculate, given reasons, the value of x. Okay. Based on the fact that they gave you this ratio, they probably want you to use this triangle. So we're using the fact that we know FC over BF is 1 over 4, and that would be equal to GH over BG. Okay, now clearly from that, we're going to have to find an expression for BG. Now, where the expression for BG is going to come from is the fact that we have the midpoint, or the converse rather, of the midpoint theorem here. So we have already proven, or we've given a reason why these two lines are parallel. But remember, the converse of the midpoint theorem, one of the other things you conclude is that this line is going to be double the size of this line. And so since we have an expression for DE, we can find BG, because we know now that BG is supposed to be twice the size of DE, because this is the bigger line. And this is because of the converse of the midpoint theorem. And so now I'm going to just fill in what we have. So to find an expression for BG, we'll say that is equal to 2 multiplied by whatever DE is. And DE is 3x minus 1. So 2 multiplied by 3x minus 1. And so BG is equal to, if we multiply in, we're just going to get 6x minus 2. Okay, so that's what BG is. Now we know that this is 6x minus 2. And now back to these ratios, because they gave you the ratios for a reason. We have a triangle here, and we have one line being parallel to one side of the triangle, so we can use these ratios. Okay, so I'm going to just use it in the same way they used it. They said FC over BF, so I'll just stick to that. So now we can say that FC over BF is equal to, what other lengths also have the same ratio? If we say FC over BF, we have to say GH over BG. And this is because of the proportionality theorem, or you could say because of a line drawn parallel to one side of the triangle. If you like, you can even say line parallel to one side of triangle. That is fine. So that is the reason why these ratios are equal. And now we already know the ratio of FC over BF. That is 1 over 4. So 1 over 4 is equal to, and then we're also going to take these lengths and put them over each other. GH is the x plus 1 over BH, which is 6x minus 2. 6x minus 2. And then now we can go ahead and just solve for x. So we can simply cross multiply. So this times that, and that times that. Okay, so you can start with the 1. It's easier. 1 times 6x minus 2 just stays 6x minus 2. When you're saying 4 times x plus 1, remember the 4 needs to multiply into both values, both terms in this. So we're going to have 4x and then plus 4. Now we just have to solve for x. So we're going to take 4 over, so that's like saying 6x minus 4x is equal to, and I'll take this negative 2 over, it becomes a positive 2, and we still have a plus 4. So we get 2x is equal to 6, and if you divide both sides by 2, finally, x is equal to 3. So that's the value of x. Okay, now moving on to the next question. Now we are on a proof. So question 9. So question 9.1 says, in the diagram, O is the center of the circle, OD bisects chord AB. This line from the center is bisecting this chord. Okay, they want you to prove the theorem that states that the line from the center of the circle that bisects a chord is perpendicular to the chord. So this is the converse of the first theorem. They want you to prove that. Okay, so here is our diagram, and we have to prove that OD is perpendicular to AB. Okay, so to prove these lines are perpendicular, I'm not sure if these proofs are in textbooks, if the converse proofs are in textbooks, but then we just have to think about it in this direction. They want you to prove that this is perpendicular. In other words, they're trying to tell you, you need to prove that this angle over here, this angle ODA is 90 degrees, and this angle ODB is also 90 degrees. So let's use the fact that we know that this is a chord. So it's also it's a straight line still. And we know that the angles on a straight line should add up to 180 degrees. Okay, so I'm just going to make this simpler. I don't want to be calling this ODA and ODB. So I'm going to just say, just to inform them, I'm going to let ODA be equal to angle D1, and I'm going to call ODB angle D2. Okay, so I'm just renaming those D1 and D2. So the fact that we know the angles on a straight line add up to 180 degrees, that is going to probably help a lot here. We're going to say that angle D1 plus angle D2 should give you 180 degrees. Okay, because angles on a straight line add up to 180 degrees. Okay, and now that we have that, all we have to prove, you see, just because they add up to 180 degrees, it does not mean that this is 90 and that is 90. We can't assume that. We can't assume anything right now. So the next thing, or the next goal that we're going to have to reach, is to show them that these two angles are equal. So that's really what we're going to be required to prove. If you can show them that angle D1 is actually equal to D2, then by default, that means that that's 90 and that's 90, so that it can add up to 180 degrees. Okay, so the fact that you just have to prove that two angles are equal, you can think in the direction of congruency. If we can form two triangles here and prove that those two triangles are congruent, remember, congruent triangles just means that the triangles are equal. Their corresponding sides and angles are exactly the same. So because of that, we're going to have to construct. So this now takes us to the way we prove the other theorem. This is the converse of that theorem, that first theorem. Okay. What we will just do is, first of all, we're going to construct this line OA. So I'm going to join that, and I'm going to join OB. And you must also just make sure to tell them any constructions that you have made. So I'm also going to say construct, rather, I should probably say it here. Construct, okay, line OA and OB. Okay, so now that these lines have been constructed, let us prove that these triangles are congruent. And so it would mean that all their corresponding angles and sides would also be equal. Okay, so to prove that these triangles are congruent, we'll just start by saying in triangle, and the first triangle is OAD. So OAD and triangle OBD. So OBD. Okay, so let's see what is equal in these two triangles. Remember, you just have to think about the fact that you have to use one case of congruency. Cases of congruency are side, 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 angle, angle, and right angle hypotenuse side. So if you can prove any one of these cases of congruency, then it means that these two triangles are congruent. Okay, so looking at these two triangles, first of all, you can see that you were already given that AD was equal to BD. So we can actually tell them that. So those are two sides in the triangles that are equal. AD is equal to BD. And the reason that these two are equal is because it has been given already. Okay, the next things that are equal in these two triangles are, you can see that OD, they are both sharing this side, OD. So OD and OD are equal, so we can say OD is equal to OD. And this is because this is a shared side, or you could also say common side. Okay, so this is a given side as well. And then the last thing that is equal in these two triangles is, if you look at OA, that is a radius, and OB is also a radius because they both drawn from the center of the circle to the circumference, so they are equal. So we can say that OA is equal to OB because their radiuses are radii, so radii, okay, which is also a side. Okay, so the reason why these two triangles are congruent, or we can say therefore triangle OAD is congruent to triangle OBD because of side, side, side. Because we have three corresponding sides being equal. And because they are equal now, because all these sides are equal, the triangles are congruent, it means that their corresponding angles are also equal. And so now because the triangles are congruent, it means now all their corresponding angles as well are also equal. So their corresponding sides are equal and angles. So this angle over here, AOD, is equal to BOD as well. And this angle over here would be equal to this angle. And so lastly, these two angles would also be equal. This angle would be equal to this angle. And so now we can conclude these two angles D1 and D2 are equal because of congruent triangles. So therefore angle D1 is equal to angle D2 because of congruent triangles. And now because they are equal, remember at start in the beginning we said that angle D1 plus angle D2 should give you 180 degrees. We can now say that again. So angle D1 plus angle D2 is equal to 180 degrees. And because they are equal, they have to add up to 180 degrees. So that would conclude that angle D1 would be equal to 90 degrees and angle D2 would be equal to 90 degrees. Okay, so that is how you can prove that theorem. Okay, moving on to the next question. The next question says, in the diagram, E, B, F, S, and P are points on the circle centered at O. GB is a tangent to the circle B. FE is produced to meet the tangent at G. OT is drawn such that T is the midpoint of EF. Okay, so this is the midpoint of EF. And then they also tell us that GO and BO are drawn, BS is drawn through T, and lastly PS is parallel to GF. Okay, so that's another important point. So I'm only looking for points like midpoints, things that are equal, parallel lines, tangents. Those are the most important things to look for. Okay, now they tell us that we have to prove given reasons that OTBG is a cyclic quadrilateral. Okay, let's highlight that cyclic quadrilateral. That thing that we have to prove is a cyclic quad. Okay, so we have to prove that this shape that I've outlined in red is a cyclic quad. Okay, so to prove that something is a cyclic quad, there are three theorems, three ways. First theorem is the case of when you have a chord that is supporting two angles at the circumference, so angles in the same segment. If that is equal to that, you can prove that this is a cyclic quad. So like if this was C and E, then that would mean that CABE is a cyclic quad if you can prove that these two angles are equal. Then there's also the theorem where you have a quad. I can't call that a cyclic quad yet. And if you can prove that the exterior angle is equal to the opposite interior angle, then it means that this shape is a cyclic quad. And then the last way to prove that something is a cyclic quad is if you have a quad inside the circle and then the opposite angles of the quad add up to 180 degrees, then this is a cyclic quad. So you can see that there are three ways to prove this, but then we have to look at which one would be the best way to use for this shape. So you have to use a way that suits the shape you have. And I'm already straight away going to go with this one because of the fact that we have lines intersecting like this. And here we also have lines intersecting like that. So it fits the shape more. So I'm going to use this one. So if we can prove that we have angles at the circumference, okay, being supported by the same chord that are equal, then this is a cyclic quad. So there are many ways to look at this. You could have tried to look at the fact that maybe this angle was equal to this angle. Or you can look at the fact that maybe this angle is equal to this angle. Or you could look at it in this way, these two angles. Or it could be in this way, this angle and this angle. And honestly speaking, this one seems more promising because of the fact that if you zoom in, they told us that this line EF, right, its midpoint is T. So we have a chord. It's definitely a chord. It's not passing the center. So we have a chord and we have T being the midpoint of the chord. So you can use the converse of the first theorem, that line from the center of the circle to the midpoint of a chord is perpendicular to the chord. So we can find out that this angle in the cyclic chord, this angle OT all the way to G, this angle OTG is 90 degrees. Okay, so OTG is 90 degrees. So the angle OTG is equal to 90 degrees. And this is because we have a line from the center of the circle to T, which is the midpoint of the chord. And that therefore means that it is perpendicular to the chord. Okay, so we know now that angle is actually 90 degrees. I think I can just, yeah. So that is 90 degrees. Okay, so OT is perpendicular to TG. Now we have to find this angle since these two were paired up. So if this angle OBG, because we have that coordinate G here, if we can prove that this is also 90 degrees, then it will mean that these angles, okay, being supported by the chord GO, those two angles are equal. So let's find out how this is 90 degrees. Well, remember that OB is a radius because it's going from the center to the circumference. And also remember that GB is a tangent. So it would mean that OB is perpendicular to GB. And because of that, it would mean that the angle OBG is also 90 degrees. So a better way to look at this is, let me rather draw a circle around this. Okay, so not the best circle, but I hope you get the idea. So we have this chord GO, and this chord is supporting the angle OBG, that angle. And then this same chord GO is also supporting another angle, supporting the angle GTO. So it's also supporting that. And so we know that they're both 90 degrees. Okay, so the thing is that it's not a cyclic chord yet. We're just proving that it is a cyclic chord. The fact that we have that angle OTG, okay, now being equal to the angle OBG, because they're both equal to 90 degrees, it will mean that this shape OTBG is a cyclic chord because it supports the theorem that states that equal angles at the circumference are being supported by the same chord, okay, or angles in the same segment. So we have proven that these two are equal, and so we can now say therefore OTBG is a cyclic chord. And our reason would be because the fact that the angles in the same segment were equal. Okay, so that's how we prove that that is a cyclic chord, the fact that they were both equal to 90 degrees. The next question, 9.2.2, they want us to prove, given reasons, that GOB is equal to S, okay, angle S. So GOB, let's look for that angle. So GOB, this angle, they want us to prove that this angle here is equal to angle S. Okay, so with these questions, the previous answer is usually very important. And that's why whenever you find an answer, it is very important to put down what you found. So you see here, we found that that's 90 and that's 90. Make sure that is put down. And now also have in mind that now this shape is a cyclic chord. We have proven it's a cyclic chord. So to find how this angle would be equal to this angle S, remember that this is a cyclic chord now. So if this is a cyclic chord, it means that, let me extend this. So it would mean that this angle BOG, so this angle, we can also find angles in the same segment for this angle as well, being supported by the chord BG, that it would also be equal to this other angle. So the other angle supported by BG, which is, will go from G to T, because this is a point on the circumference, down to B. So it would also be equal to this angle over here. Let me rather mark that in red. So now we know, okay, these two angles are equal as well because this is a cyclic quadrilateral. And this is angles in the same segment are equal. So this angle they spoke about, GOB, so GOB is equal to the angle GTB. So GTB. Okay, so now that those two are equal, let's see what else we can use. We have to give a reason because of angles in the same segment as well. Okay, and now that we have that, let's zoom out and see what else do we have in this diagram. They also gave us that these lines are parallel. So we have this is parallel to this. So those two lines are parallel. And because those two lines are parallel, if you draw an upside down F here, you'll see that we have corresponding angles. So this angle, angle S, is equal to this angle, angle GTB. So we can finally say that angle S is equal to the angle GTB because of corresponding angles on parallel lines are equal. Okay, now that we have that down, so since they're both equal to the same thing, they're now both equal. So angle GOB is now equal to angle S. So that is that question. Question 9 done. Now we move on to question 10. Okay, so in question 10, which is the last question of this paper. So this is what we have been given in this question. They tell us that in the diagram, PQRS is a cyclic quadrilateral. KP is a tangent to the circle at P, C, and D are points on the chords. KP is a tangent to the circle at P, so here's KP being a tangent at P. C and D are points on the chords PQ and PS, so those are just points on the chord. And CD is produced to meet RS produced at A. CA is parallel to QS, so CA being parallel to QS, okay. And then they say that RC is drawn, and they told us that P1 is equal to R2, so these two angles are already equal just because it's given. So the first question is, we have to prove, given reasons, that 10.1 S1 is equal to T1. In order to prove that, when they give you a diagram that doesn't have numbers, sometimes it is helpful to let one of this angle be equal to something. For example, I can say let S1 be equal to X. That way you'll be able to follow the angle as it goes on, as you find out what other angle it's equal to. So I'm going to actually say that here. I'll start from S1. Well, you can start from either one. You can start from S1 or angle T2. And angle T2, I feel like that is better to use because we have parallel lines. This one can move more easily. Angle S1 is sitting here as the exterior angle of this cyclic chord. And like the only way that it can move is to be equal to the opposite interior angle. So in this case, I'm going to let angle T2 be equal to X. So I'm going to say let angle T2 be equal to X. And so I'm going to follow it like that. I'm going to call this X and see what else is equal to X. So as long as you can find a way that this ends up being equal to this, in other words, that angle S1 ends up being equal to X as well, then you've proven that they're equal. Okay, let's just see how many marks is this for? 4 marks. Okay. Okay, so with Euclid and with this type of section where they don't give you actual angles, it's not really a guessing game, although I cannot say that you can't find the answer if you don't guess. Sometimes you find the answer when you guess. You can be that lucky. But most of the time you need to have a strategy in this. Okay, so because of the fact that they gave us another angle, they told us that P1 was equal to R2. Okay, so P1 and R2 are equal. Since those are equal, it would mean that, well, you could also find that maybe P1 is also equal to something else in the diagram other than T2. So because of that, I'm also going to give this one a name so that I can also monitor it. I'm going to call P1 Y. So I'm still going to tell them and, so let T2 be equal to X and angle P1 be equal to Y. And so because angle P1 is Y, by default, it would mean that R2, I can also call that Y. So the whole goal here is to find this angle, okay? And basically this angle should say X. It should be equal to X. Okay, so there's two directions that you can look at this thing. You can look at this angle and try to make it equal to other angles. Like we have parallel lines here, and this now will be equal to this. But then that would be like guessing, because then now we're just, okay, this is equal to this. And then we're just trying to see what else is equal to what and hope that we somehow find this. But it would be better to actually work with a plan. And this is where the plan comes. We know that we have to find out why this angle is equal to this angle. But we also know that this is the exterior angle of a cyclic quad. And so it's going to be equal to the opposite interior angle. So basically, we know that this, and I'll just put that in a different color rather. We know that this angle is equal to this entire angle. So if we can find out what angle Q1 and Q2 are in terms of X or Y or X and Y, then we'll be able to find out what this is by adding them together. Then we'll find out what S1 is. And I know the question says that we have to prove that they're equal, but if they really are equal, then when you add them together, they should give you X, since we're trying to prove that S1 is equal to T2. So my goal here, or my plan here, is to find Q1 and Q2. Okay, so with Q1, the fact that you have this tangent KP, so I can see that we have this line PS, which is a chord, and it's the chord that is helping to support this angle at the circumference. So it means that the angle between the tangent and the chord is equal to the angle supported by the same chord. So this angle Q1 is equal to Y. Okay, so we can just state that down now. Know that, okay, because of that tan chord theorem, but you have to write the theorem in full. So remember that angle has to be at the circumference. If it was at the center, that doesn't make them equal. Okay, so I'm almost there now. I just have to find Q2. Okay, so I see something that I can use for Q2. You see here we have, and now just put this in blue, we have a triangle. So there's a triangle over here. And this triangle has T2 as an exterior angle. And so the exterior angle of the triangle is always equal to the sum of the two opposite interior angles. So we're just trying to find an expression for Q2. So now I know that angle, and let me just name it, angle T2 is equal to angle R2 plus angle Q2. It's equal to angle R2 plus angle Q2. And so I just put the reason, exterior angle of a triangle. Okay, so it's equal to the sum of the two opposite interior angles. Okay, so angle T2, that was X. So we have that, that's X. And that is going to be equal to Y plus Q2. So it's equal to Y plus Q2. Okay, plus that. And so we just have to make Q2 the subject. So Q2 is equal to X. And then we take Y over minus our Y. Okay, so we have something for Q2 now. So Q2 is X minus Y. So now that Q2 has been named X minus Y, remember the whole goal of this is, since I had an exterior angle here, it's equal to this opposite interior angle. I just have to add Q1 and Q2 together. So I'm going to say that Q1, or I'd rather just get straight to the point. I'll say angle S1 is equal to angle Q1 plus angle Q2, because together they form the opposite interior angle. So, and that's because of the exterior angle of a cyclic quad. Okay, so the exterior angle of a cyclic quad is equal to the opposite interior angle. And so now it means that angle S1 is equal to angle Q1, which is Y. So Y plus angle Q2, which is X minus Y. X minus Y. So if you simplify this, you can see that Y is positive and Y is negative. They cancel. And so angle S1 is finally equal to X. And remember what else was equal to X? At first, we made T2 equal to X. So it means that therefore angle S1 is equal to angle T2. So there we go. That is how we prove that one. So you see, it's not really a guessing game. You have to form a strategy as you're going on. So now I'm going to go ahead and call this X. just so that everything is sorted out for the next question, because the next question may have a lot to do with what you did here. So the next question is now, okay, so we have 10.2. We need to prove given reasons that AD over AR is equal to AS over AC. So first of all, mark these lines and find out where are they coming from. Are they coming from a triangle? Are they coming from the proportionality theorem? Because we have parallel lines. Okay, so I'm just going to get rid of some lines here, like that triangle. Okay, so let's mark these lines. AD is this line, AD, and they're telling us over AR. So AR is this line, and then AS is here, AS, the shorter line, and then AC is just that long line here. Okay, so the thing about this, where you have proportions being over each other, you have to find out, is it part of two triangles? Because if it's part of two triangles, it's probably a case of similarity, where you first have to prove that the two triangles are similar and then put their proportions over each other. So if you look at the lines that have been named, we have AS, and AS is part of this triangle ASD. They also named AD, so that's two lines in this one triangle ASD. Then they also named the line AR and AC, and we can see that that is part of the triangle ACR. Okay, so it's probably a case where these two triangles are similar. Now, the good thing about this is that they are sharing one angle. They have a common angle here, a shared angle. So we have to find out how these two triangles are similar. So I'm just going to outline the two triangles. Okay, so it's the blue and the red triangle. So we're going to have to find out, how are these two triangles similar? First of all, if we have X here, then one of these angles should also be X. So if we look at this one, angle R1, well, if these two lines were parallel, then, that would be X, but it's not. So it could be R1, but it could also be C2. They don't always put it in the right order for you. They will not always put it as, okay, if these two angles are the same, then these two angles are the same. They won't always do that. So which of these two angles can easily become X? It will actually be C2, because here we have X, we have parallel lines. If you see that we have alternate angles here, it would mean that T2 is equal to C2. And so this would also be X. So we can actually state that down first. So I'm going to put these two triangles and let's see how they can become similar. So this one is definitely also going to be X. And because this one is X and we have a common angle, it will mean that angle R1 and angle D1 is just the third angle in both triangles. So the fact that we have it in this order, it means that these triangles are similar like this. ASD is similar to triangle ACR. You see, from the common to the X to the third angle, common to the X to the third angle. So we can go ahead and start proving that these two triangles are similar. So in 10.2, I'm saying that in triangle, and I'll name it in the right order since I can see that they are similar in that order. In triangle ASD and triangle ACR. And now we can start proving that these triangles are similar. Okay, so first of all, we have a common or shared angle. So angle A is equal to angle A. We can say shared angle. The next thing that is equal, we have this being equal to that. Now, I know I just put an X here, but I have to actually tell them why they're equal. So I'm going to tell them that angle C2 is equal to angle T2. So angle T2. And the reason was because of we have alternate angles on parallel lines being equal. And now that they are equal, I can now therefore say that now angle C2 is finally equal to angle S1. Okay, and the reason they're equal is because we've already proven above that T2 was equal to S1. So here I'm just saying therefore these two are equal. Okay, so we have this and it's really just proven. Now the last angle in the triangles that are equal would be this angle in the blue triangle D1 and angle R1. Okay, because they are the third angle in the triangle. So D1 is equal to angle R1 and its third angle in a triangle. Okay, so therefore triangle ASD is similar to triangle ACR, and the reason that they are similar is because of angle, angle, angle. Okay, and now that they are similar, I can use these lines that they've given. Now that I have that, I'm going to only pick the lines that are in here. I first see AD, so I'm going to take AD. Now AD has to go over whatever corresponds in the next triangle. So if I say AD, I have to say AR. So it has to be over AR. And that's going to be equal to, I have AS here. So I'm going to pick AS. I'm saying AS over, and I have to take AC because it has to correspond over AC. And that's exactly what they wanted. And so we've proven this, and the reason why these are equal is because of similar triangles. Okay, so that's 10.2. And then we are at the last question, 10.3. Okay, so let's look at what we have in this. They told us that AC times SD is equal to AR times TC. So one of the things that you can do is look at the triangle that you had and check if these sides are on those triangles. So AC, when we look at AC, AC is here, AC, it's on the red triangle. So, okay, at least this one is here. SD, SD is also on the triangle. Okay, it's on the blue triangle, the smaller triangle. So we have that at least. AR is also on the triangles, the red triangle. And then TC, TC, okay. So that one is the only one that is not in any of these triangles. So I'm going to actually highlight that one. TC. It's probably a situation where we have to find an expression for TC, okay, using something else. So since we know we have these ones in the triangles, let us actually go and find them here in the proportions. So I'm looking for AC, and AC is going to go with, so if I want AC, it's from this triangle, AC, I'm going to have to take AC over AS. So I'm saying AC over AS. Or I can just write down all the proportions. So AC over AS is equal to, we also have an SD. Okay, I'll just continue with this. SD. If you say this triangle, okay, a side in this triangle over this one, you have to continue in that order. So I know I'm seeing SD, but I cannot say SD over CR. That would be wrong. I have to start here. So I'm saying CR over SD, CR over SD. And I just want to see all the things that it's equal to. So I went AC, those two, CR and SD, and then last will be AR and AD. So AR is over AD. So these are the proportions that we get from the triangle. And in these proportions, the ones that we have here in what we have to prove, we have AC, we have SD, and we also have AR. But as you can see, they are not from a pair, they're from the three proportions. I can see a way to include TC, but it's not using these triangles anymore. It's using the fact that we have this triangle RAC and a line being parallel to one side of the triangle. So we can use the proportionality theorem on this. Okay, but let it include lengths that we have here in what we have to prove. So if you look at this as RA or AR, okay, we can take that over AS because here we have AR and we also have an AS. So if I could say just AR over AS is equal to, and then I have to go in the same order on this triangle as well, on this side of the triangle. So I'm taking AR, meaning this length, over AS, meaning over this. It should be equal to, on this side, CR, okay, CR over, and remember I took AS here, so here I have to take CT, okay, or TC, TC. So, and this is because of a line drawn parallel to one side of the triangle. Okay, and then I'm going to cross multiply these now so that it can sit like that. So I'm going to have AS multiplied by CR is equal to AR multiplied by TC. Okay, now with the way this looks, it almost looks like this. Well, it has the one side, has this side now, AR and multiplied by TC. It's just this side that is different. So in these proportions of the similar triangle, let's see if we can find something for these. Okay. And I can actually see here we have AC, and SD. Okay, so we can multiply and we'll have AS and CR. So let's actually take those proportions. I'm taking AC, so I can only say these are equal because of similar triangles. So AC over AS is equal to CR over SD, and this is because of similar triangles. Okay. Now I'm going to cross multiply. So I have AC being multiplied by SD, and that is equal to AS multiplied by CR. Okay, so now I have this side. And now if you look in both of these equations that we have an AS and a CR and an AS and a CR. So it means that we can equate these two. We can say, therefore, we know that AS times CR is equal to AS. So AS times CR here is equal to AS times CR here. And so this would be, since AS times CR was equal to AR times TC, but I want to put it in their order. So I'm going to take it like this. I'll rather say AS times CR here was equal to AC times SD, and that would be equal to, here we had our AS times CR, and that was equal to AR times TC. So AR times TC. Okay, and that is what they have. Yeah, so that's how they got that. They got it using the similar triangles and the fact that we had that triangle and a line drawn parallel to one side of the triangle.